Hello everyone, I'm Mimoun Mohamed and I will be presenting a joint work with François Malguir, Valentin Mia, and Caroline Chou on when through meets sparse recovery, the support exploration algorithm. Nowadays, when you implement a neural network using a favorite library and programming language, the library constructs what we call a computational graph. For a one-layer perceptron used in a learning task like regression or classification, the graph looks like this. Your data is first multiplied by a weight vector, then a bias is added, and finally, the result is compared to the true labels or values using a loss function. Like in any learning task, the library computes the gradient of the loss with respect to the weights and the bias we want to learn here, and updates them using the backpropagation step of a gradient descent algorithm. To do this backpropagation step, we need to be able to compute the derivatives of all the operations in this graph. However, a problem arises when non-differentiable operations like quantization function are included. Here, you see the graph of a round function, which quantizes a real number to the closest integer. The derivative of this function is either 0 or undefined, making learning through backpropagation impossible. To address this issue, we use what we call the through estimator, or STE. The STE approximates the quantization function as the identity function during the backward pass. This means that during the forward pass, we apply the quantization function, but during the backward pass, we replace its derivative with the derivative of the identity function, which is 1. In our work, we do not use the STE to deal with the quantization function, but to address other non-differentiable operations such as sparsification. Our problem is the following. You have a sparse signal x star which you want to recover from an observation y. Here, sparse means that the signal x star has only a few non-zero entries, fewer than a known value k. The observation y is a product of the known matrix A on the signal x star plus some noise. The goal here is to recover the support of the signal x star, which is a set of indices with non-zero entries. To do so, we aim to minimize the mean square error between the observation y and the product of the matrix A and the estimate x, under the constraint that the estimate has at most k non-zero entries. However, this sparsity constraint makes this optimization problem NP hard due to its combinatorial nature. To tackle this, we proved in our paper that we could replace the constrained minimization of f with an unconstrained minimization of the composition of two functions, f and h. Here, instead of optimizing over the space of k-sparse vectors, that is a set of vectors with at most k non-zero entries, what we do here is that we optimize over the space of all vectors, and we use the sparsification operator h to project the full vector into the space of interesting k-sparse vectors before computing the loss f we want to minimize. Since the sparsification operator is not differentiable, we cannot use the gradient descent algorithm directly. So, we use the through estimator to replace the derivative of the sparsification operator h by the derivative of the identity function, which again is 1. Thus, if you want to write a gradient descent algorithm to minimize the composition of f and h, you can first use the chain rule to replace the gradient of the composition by the product of the gradients of f and h. Then, using the STE technique to replace the gradient of h by 1, you can compute the gradient of the composition as the gradient of f computed at the sparse estimate. This leads to the iterative scheme of the support exploration algorithm, which can recover the support of the signal x star. Our contributions are the following. Our algorithm extends the STE for quantization to the sparse support recovery problem. In our paper, we show that this algorithm can explore beyond local minima, and our experiments demonstrate good performance in challenging cases, such as when the matrix A is frontally coherent as in spike deconvolution. Finally, we derive the theoretical guarantees for the super recovery performance of the algorithm under a restricted isometry property assumption on the matrix A. I invite you to read the paper and would be happy to meet you at the poster session.